Good morning, sir.
Okay, so today we are going to continue with the introduction. I'm going to explain today also about the error and how to make the error analysis, and also how to quantify and control the error it's coming from the numerical methods. Just only to refresh back your mind. Remember that previous class we were talking about the relative error, and there's also another error we call it, it's the approximate error. So we were saying that if you are going to talk about the relative error, the question, or you need to have the true value. So the true value is going to be provided. So if you have the true value, so you can calculate the relative error. In case that you don't have the true value, you cannot access the true value, so that's meaning you are going to calculate something we call it, it's the approximate error. So it's the new result minus the old result over the new results. And remember that there is no error in negative. That's why here this is a model. Okay, so continue with the error. We are going to see today it's Taylor series expansion, which is going to be helping us to deal with the truncation error. But before we start, it's what actually is the truncation error. So truncation error, it's considered like the discrepancy introduced by the fact that numerical methods may employ approximate to represent exact mathematical operation and quantities. By the way, all these 3 points, 1, 2, and 3, they are having the same definition of the truncation error. So truncation error also, I can say it's the error, it's resulted from using an approximate solution in a place of exact mathematical procedure. Or also you can say it is like the difference between the calculated value using the exact mathematical equation and approximation mathematical equations. If you are not following what I'm saying in here, if we back to the first example that we have taken before, remember, we were talking about our first example of these parachutes, and we want to calculate the velocity of these parachutes. When we are solving it using this equation, we are saying that this one is considered it's the analytical solution, or this is the exact solution. After that, we are saying that it's most of the time, unfortunately, there's many mathematical models cannot be solved exactly. So we are going to try to approximate the solution. So when we approximate the solution, we are taking into account the previous state of any objects or the properties in previous, and we take it into account inside the calculations. So we came up with the approximate solution. So this gray line here, this is the exact solution. And the black line with the dots, this is considered is the approximate solution. The difference between them, between the exact solution and the approximate solution, this is what we call it here, it's the truncation error. So now if you are going to read the slides back again, you'll understand what he's talking here about. Truncation error, it results from using an approximate solution in a place of exact or analytical mathematical procedure, or the difference between the calculated exact or analytical solution and the approximate mathematical equations. Okay. So what actually is the Taylor series? Here we are saying that is truncation error and the Taylor series. So what's the relations between the truncation error and the Taylor series? So Taylor series for you is considered is a tool or a means that is going to be helping us to predict a function value at one point in terms of the function and its derivative. So in this case here, when the question is coming out, which is I said that you're not going to have question coming from this introduction, but in case that, because we are going to have this one in advanced chapter, the question when it's coming from this part, you're going to have an initial value of x. So this is going to be given. And also you are going to have a function at the point of x. So you are going to have these two parameters. So Taylor series means predicting a function value at one point in terms of a function value and its derivative. So now, when we are talking about prediction, or we are making approximate, since this value is given to us as an initial, that means I want to predict what's the value of the function at the coming point. My coming point here is x plus 1. So I want to predict, I want to know what's the value of the function when x plus 1. Let's say, for example, if x here is equal to 0, this is 0, and your step size it's equal to, so this means x plus 1 in here, that means is 2. 0, your step size is 2, so that means x plus 1 is 2. So now I want to know what's the value of the function when x is equal to, and what's the value of the first derivative of the function when x is equal to at this point, and what's the value of the second derivative of the function when x is equal to 2. So this is the meaning of trying to predict a function value at one point in terms of a function value and its derivative to another point. So this is the Taylor series. So what you're going to notice in here, Taylor series, it has many orders, from 0 order to n number of orders. If the question is asking you to find what's the predictions of the function at one point in a form of 0 order, so the prediction of the function is going to be equal to the function itself. And you can see it from here. This is x, this is the function of x. If I want to predict from x plus 1, so I'm going to get the function itself at the same point, which is 2 here. So the 0 order of Taylor series, it's the function itself. If talking about the first order of the Taylor series, you are going to add one more term. So the function of x plus 1 to be predicted at the first order is going to be equal to the function itself plus the first derivative of the function times the step size. So now we added one term, which is the first derivative of the function and the step size. Okay, if we are talking about the second order of the Taylor series to be predict, so it's equal to the function itself plus the first derivative of the function times the step size time plus the second derivative of the function over the factorial of 2 and step size squared. So now I think you can imagine if this question is asking you to get the third order. If the third order, so this means you need to get the function plus the first derivative of the function times the step size plus the second derivative of the function over the factorial of 2h squared plus the third derivative of the function, so 1, 2, and 3, x over the factorial of 3 times h cubed. And you are going to continue like this till you are going to reach the nth order of the Taylor series. So in general, Taylor series is going to be something like this. Okay. So, but here there is a term here, we call it it's Rn. I'm going to explain what does it mean, the Rn, right now. Okay. So Rn, we call it here, it's the remainder of the Taylor series expansion. So the remainder terms Rn accounts for all terms from n plus 1 to infinity and can be designated with this mathematical model here. It's also expressed as Rn is equal to OHn plus 1. So in case that we are going to say that if we are going to truncate the Taylor series expansion after the 0 order terms, so we're just only going to take 0 order terms from the Taylor series. So that means the remainder that we are not calculating it is going to be starting from the first order of the Taylor series to the nth number of the Taylor series. Of course, you don't understand what I'm saying in here, but let me explain it in detail. This statement saying here, let's say we are going to truncate the Taylor series after the 0 order. Okay, if we back to this figure here, we are saying that the 0 order of the Taylor series is the function itself. This is the one. And this is the whole terms of the Taylor series. Okay, so now the slide says, let's say we are going to truncate the Taylor series after the 0 order. So that means from the Taylor series, you are going to just simply going to take this portion for calculation. So you're going to take this part. This is considered is the 0 order. So you're going to end up with this term, the function xi plus 1 will be equal to the function itself. And if you are looking at the slides in here, let's say we are going to truncate the Taylor series expansion after the zero order, we are going to yield or get the function itself. And exactly this is what happened here. We get the function itself. Okay, the rest here from this portion to the end, this is considered as a remainder. We didn't take it into account for the calculations. So now the remainder terms from the zero order will be equal to the first derivative of the function and so on. And when we back here, we are going to find it's the first derivative of the function till n number of the function. Okay, I will give you also another example from a real life. It's going to be clear of how these things it's really important and how these things will help us to quantify the error. And what does it mean really is the remainder. Okay, let's say that you are, you came to me suddenly like, sir, I have a problem and I want to borrow from you 10 ringgit. Okay, so you came to me, you have a problem, sir, I am going to have a problem and I want to solve it and just only need to borrow money from you. Just give me 10 ringgit, it will solve my problem. So I said, okay, I give you the 10 ringgit. And you promised me that you are going to pay me back the 10 ringgit, but in a form of patches. So this means you are not going to give me 10 ringgit directly. You are going to make it as a cut, as a patch. Maybe one day you will give me 1 ringgit, the second day you'll give me 2 ringgit, third day you'll give me 3 ringgit. So now take this scenario with me. If your first time, or from the zero order, or the first day, which is we call here, it's the zero order, you showed up to me and you give me 2 ringgit only. I give you 10 ringgit, but you showed up on the first day, you give me 2 ringgit. So that means my error here is 8 ringgit. I still have a balance, which is we call here is the error or the remainder, it's 8 ringgit. Okay, so when you give me just only 2 ringgit, the error is 8 at the zero order or the first day. So this is 2 ringgit and the error is 8. If you didn't show up after that, the second day or the third day, so my error is going to be all these values, 8 ringgit. I rugi for that. Okay, so this is the zero order. And these things here from first to the third, consider a remainder. Now, if you add one more day, so if you showed up on the second day, which is the first order, and you add me also 3 ringgit, still my balance 10, so that means my error here is 5 ringgit. If you show up also the third day and you give me 3 ringgit, so my error is going to be 2 ringgit. If you show more days, so you give me also 1 ringgit, so my error is going to be here, it's 1 ringgit, till I get my all money in here. So now you can see here from the Taylor series, the more when you are going to make a calculation for the Taylor series, if you add more terms for the calculation, so this means if you are not just only stop at the zero order, let's say that you are adding for your calculation the first order, or you are also adding the second order, the more you are going to reduce the error. If you just stop at the zero order, the error is going to be huge, which is the value of R or the remainder is going to be really huge. That means you are not taking into the calculations. Same like the example I giving you in here. If you give me just only one shot of the borrowed money, my error is going to be very high. But the more you are giving me back or you are adding for the Taylor series, the more you are reducing the error. Is it clear? Do you want me to repeat anything in here? Any question?
No, sir.
Okay. So this slides in here, it's just only explaining the remainders of the Taylor series expansion and showing you the. Okay, this one. It's showing you the predictions of the function from x to x plus 1 to get the value of the function at these points. If you take into account the zero order, so that means you are going to get this value. And the difference between the zero order and the value of the function itself, this is considered is the remainder because it doesn't take into account. If you take the second order, the third order, the fourth order, the fifth order, so you are going to get the exact value. Okay. Let's see again here. Okay, this is the last part of our introduction today. We call this one, it's the numerical differentiation. This part in here, I'm going to give you a brief about it, and we are going to solve a little bit of example and exercise. But this part or this chapter, we are going to repeat it again at week 10 or week 11. So just focus on it. You are not going to have a questions coming in from this part, but at week 11 or week 10, we are going to repeat this one with high accuracy value. But it's better to have an introduction about it right now. Numerical differentiation, it's trying to predict the value of the function at 3 points: forward points, backward points, and center points. And also, this is numerical differentiation. It has the relation with the Taylor series expansion. So the forward finite divide difference, it starts with the initial value of x. So x value is going to be given, and the value of the function also is going to be given. Since we are talking about the forward finite divide, so this means we need to predict the function at the coming point. So I'm going to try to predict the function at x plus 1. So I want to know what's the value of the function at x plus 1. So this one here from x to x plus 1, that's why we call it is forward finite divide. And you can see that from x to x plus 1, this is considered as a single step size, h. Okay? If we are taking the same, but in a form of the backward finite divide, so this means we are starting from x, but here we are trying to find what's the value of the function at x minus 1. So we go backward. So this is also considered a single step size because from x to x minus 1, this is considered a single step size. If we are saying that about center finite divide, so it's from x to x plus 1 and from x to x minus 1. We are trying to find the value of the function at these 2 points in here. The function at x plus 1 and the function at x minus 1. And this one is going to be more accurate because here we are taking 2 step size, 2h. Okay, remember we are saying for the Taylor series expansion, the more you are adding terms for your calculations, the more you are reducing the error. So if you compare the forward finite divide or the backward finite to the center finite divide, it's more accurate because it's 2 step size. From x plus 1 to x and from x to x minus 1. So we are adding 2 terms from our calculations to get a value. Okay. In here, there will be a functions or an equations is going to be provided. So in our course, actually, you are not going to memorize any equations. All the equations for test 1 and also for the final exam, it's going to be provided. So now let's see how it looks, the equation for the forward finite divide. Remember, we are saying that for the forward finite divide, you are talking about x to x plus 1. So to predict the function, so it's going to be x plus 1 minus x. And this is here is the function of x plus 1 minus the function of x over single step size. This is considered h, step size. If we are talking about the backward, so this means the function of x minus the function of x minus 1 over the step size. If we are talking about the center finite divide, remember that it's from x plus 1 to x minus 1. So that's why the equation is the function of x plus 1 minus the function of x minus 1 over 2 step size. Okay, so the difference here is this is single step size. Here, this is a single step size for the forward and the backward, but for the center, we are talking here about 2 step size. We have an example here. I'm going to show you the solution of the example, and there's an exercise. You are going to do it by yourself, and you are going to compare your answer. So this example asking here to use the forward, backward, center finite divide to approximate or to estimate the first derivative of the function. So this is the function is given in here. The initial value of x, it's given, it's equal to 0.5. And your step size here, h, it's 0.5. And the example also asking you to repeat the same example when h is equal to 0.25. So now let's start with x 0.5 and the step size is 0.5 with this function and see how is the answer is going to be for the forward, backward, and centered. Remember that we said it's centered finite divide. It's more accurate because it has more terms for calculations, not just only single step size. Okay. My true value that I want to achieve supposed to be the answer of this one for the first derivative. It's negative 0.9. So I have the true value. So each time I make a calculation, I can calculate the relative error. True value minus the result over the true value. So now my step size is 0.5. So x is equal to 0.5. This is given in the example itself. X, it's equal to 0.5 is given. Okay. So that's mean if my step size h is equal to 0.5, my initial value of x is 0.5. So to go forward with the single step size, so x plus 1 will be equal to 1. Now, if x is 0.5, I will go backward. So this means x will be equal to 0 based on the step size. 0.5 minus 0.5 is 0. 0.5 plus 0.5 is equal to 1. So this is the backward, and this is the forward. So remember that we already have the points. So this means we are having these points now, x plus 1, and x minus 1. So now I need to find what's the value of the function when x plus 1, and what's the value of the function when x plus 1. So I need to find these 2 points, this point and this point. So when x is equal to 0, so I'm going to put zeros in all the x's here. So when all the x's here is equal to 0, the function will be equal to 1.2. Now I want to see when x is equal to 0.5, what's this function is going to be here. So I will put 0.5 in all the x's here. So I will replace 0.5 in all the x's to see what's the function will return when x is equal to 0.5. So the answer is 0.925. And when x is equal to 1, this function will be equal to 0.2. Is it clear what I am doing here?
Yes, sir.
Okay. In this case in here, we are not yet predicting what's the value of forward, backward, and center. To predict those values, I need to use these equations in here. I want to use these equations to find the forward. I need to use this equation to find the backward. I need to use this equation here to find the center. So for the forward finite divide, I need to find the function of x plus 1 minus the function of x over xi plus 1 minus x. So that's mean 0.2 minus 0.925 over the step size. So now let's see it. For the forward finite divide, it's going to be 0.2 minus 0.925 over single step size. So the answer is negative 1.49. When we are looking at this answer here, compared to the true value, it's too far from the true value. It's not even matching. So the error is going to be huge. So now I can calculate the error. True value minus this result over the true value. So the answer is going to be 58.9%. The error is 58.9%. So now let's try to find for the backward finite divide and we'll see what the answer is going to be. So for the backward finite divide, so it's going to be from x to x minus 1. So this means 0.925 minus 1.2 over 0.5. So the answer is negative 0.55. Again, look at this value and the true value, still far from the true value, is not even matching. So that means the error also is going to be a little bit huge. So the error, true value minus the result over the true value times 100. So it's 39.7% still. Remember that I said, now when we are going to talk about the center finite divide, the error will be less than forward and the backward. Why? Because we are having two terms, from x plus 1 to x and from x to x minus 1. We are taking two terms as a Taylor series. The more you add terms, the more you are reducing the error. So the equation is going to be from 0.2 minus 1.2 over 2 step size. So 0.2 minus 1.2, these two values here, over 2h. 2 times 0.5 is 1. So the answer here is -1. When you are looking at this answer here, and somehow closer to the true value. That's why when you're going to calculate the error, you're going to see the answer of the error. It's 9.6% error. So it's more accurate. Remember, it's the example here asked you to do this one and repeat when the step size is 0.25 to compare the answer. So now we just follow the example of 0.5, step 0.5. Now let's repeat the same example, but with the smaller step size, 0.25, and see how is the answer is going to be. Is it going to be written a better value or no? Now the step size is 0.25. Of course, we are starting from the same initial value, 0.5. So when I go for the forward, 0.5 plus 0.25, 0.5 plus 0.25, so this means for the forward, it's going to be 0.75. If we go for the backward, 0.5 minus 0.25, so it's 0.25 for the backward. So now I'm going to find the function for each value. When x is equal to 0.25, the answer is 1.103. And when x is equal to 0.5, this function will be equal to 0.925. And when x is equal to 0.75, the function is going to be equal to 0.63. And again, I'm going to try to find the forward, backward, and center. So for the forward finite divide here, the answer is going to be 0.63 minus 0.25 over 0.25. 0.63 minus 0.925 over single step size. So the answer is -1.15. Compared to the true value, still there is an error. But if you compare this error to the step size of 0.5, so this one is more smaller because we reduce the step size. For the backward, you are getting the answer of -0.714. Compared to this one, still there is an error. So the error here is 21.7. But it's the more accurate answer when we are talking about the center finite divide. 0.63 minus 1.103 over 2 step size. So this value minus this value over 2 step size. So the answer here is -0.934. Look at this value and look at the true value. And somehow they are closer to each other. That's why when you are going to calculate the error, you are going to see the error is 2.4. So when you are reducing the step size, also you are reducing the error. Okay, there is an exercise. You can do the exercise by yourself, and the results it's already mentioned in the slide, so you can compare your answer when you are going to do the exercise by yourself. If you have any questions, also you can ask me about it, how to do the exercise. So this is for yourself. So before I end up this class in here, or we can skip this to here. I need to talk now here about the total numerical error. When you are doing any mathematical or any numerical calculations, the total error from the numerical, it could be happen because truncation error, because you are approximating the results, or because the round of error. The round of error because it's the number of the significant figure that you are using for your calculations. Whether you're using 2 significant figure or 4 significant figure, still there will be some round of error. So how to control the round of error? To control the round of error or to reduce it, it's by increasing the number of the significant. The more you are increasing the number of the significant figure, the more you are reducing the error. And also by reduce the number of calculations or computations in analysis. So this is how to reduce the round of error. But to reduce the truncation error, you need to decrease the step size, same like the example we have done just right now, from 0.5 to 0.25. When you reduce the step size, it's reducing the error. So truncation error will be reduced or be decreasing the step size, or by increasing the number of calculations. As we see that if you are adding more calculation from the Taylor series, the more you are reducing the error. But when you can see from here, this computation analysis, if you are increase it, the round of error will be increased because the computation analysis here to be reduced. So round of error and truncation error, they are contradicting with each other. So you are not again to reduce both of them at the same time. Round of error doesn't like to do a lot of calculations, but truncation error does like to do a lot of calculations. So what you need to do here to control the numerical error, avoid to subtract two nearly equal numbers, so you are going to avoid lose of any significant figure. For truncation error, it's better to use a Taylor series and add of round of error analysis to add more terms for calculations. And also, when you are performing any numerical experiments, try to change or use different step size to see the result is coming out is going to be better or not. Okay, so that's all for the introduction of the numerical methods. Next class, we are going to talk about the first chapter of the numerical method, which is the finding the roots of the equations. This is very important class because question number 1 at assignment and test 1 midterm and also at the final, it's coming from this chapter. So hope to see you all fully class on next Monday. If you have any questions about the introductions, how to do the calculations, you can ask me anytime. I hope also you are going to try the example by yourself, which is this one. I hope you are going to try the exercise by yourself. And if you have any questions, you can ask. Before you leave, I want you to write your name and also your student ID in the chat box. Any question? Any question about the introduction?
No, sir.
Okay, thank you. So please write your name, your student ID at the chat box for the attendance today. Thank you very much. See you inshallah on Monday.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Bye-bye.
Thank you, sir.
Welcome. Bye-bye.
Thank you, sir. Thank you, sir.
Thank you. Bye. Take care. Bye-bye. Have a good weekend.